Guilloud. Yes. Yeah. Thanks for the introduction. So I'll tell you in that talk a little bit about orthologic and why it can help with formal reasoning. So I know it's the very last session of the day. We're all a bit tired. So let me first describe you why you may want to be interested in orthologic, and so why now is a good time for our last burst of energy. So I'm sure we all agree that reasoning in propositional logic is generally useful for a wide variety of applications, program verifiers, proof assistants, compilers, type systems, optimization problems, many more. I'm sure you all have your favorite use case of deciding if a certain formula is true or not. But unfortunately, that's in general also a hard problem to solve. Typically, the validity problem for classical propositional logic is co-NP complete. So we tend to use heuristics, which are very useful in practice, but which are also limited because of their unpredictability. They may depend on your exact computing power, sometimes non-deterministic factors. In general, they offer you very few guarantees about what they can and can't solve in a certain amount of time you're ready to give them. So the question is, can we somehow design algorithms which are guaranteed to be efficient and always predictable with respect to some theory that is sound with respect to our basic theory, but also well characterized? An example of where we can do that is when we take the system F-type system and restrict its polymorphism to top level only to obtain decidable type inference. So for classical propositional logic, we could try to solve the problem inside inducionistic logic. It would certainly be sound, but in terms of efficiency, it's not better, because deciding the validity problem here is p-space complete. So we have another proposal, orthologic. So orthologic is a propositional logic with conjunction, disjunction, and negation, and its underlying structure, its Lindenbaum algebra, is that of ortholattices. So classical logic corresponds to Boolean algebra, the way that intuitionistic logic corresponds to hating algebra, and the way that orthologic corresponds to ortholattices. So what are ortholattices? Ortholattices are algebras, in fact, lattices, which satisfies a set of axioms that you can recognize, and they're duals. So you have the commutativity rule, associativity, idempotence, the laws about the constants 0 and 1, double negation elimination, the law of excluded middle, the Morgan's law, and the absorption law, which make the whole thing into a lattice. But crucially, it does not in general satisfy the full distributivity law. In fact, if you added distributivity to these laws, you would obtain a Boolean algebra. So the kind of problem we want to solve is this. Let's be given some statements that we know that we assume are holding. For example, this first formula here. Does this other formula at the bottom hold? So you can try to figure out in your head if it does hold in classical logic and if you need distributivity for it. It's not so easy to do by head, but actually, yes, it is true in orthologic. And hence, it's also true in classical logic. I could explain you why that follows. So now the question is orthologic as a logic, as a theory, an interesting one to solve problems? And can we decide such problems efficiently? So we argue that, yes, orthologic has good properties to solve problems, properties that are both algorithmic, proof theoretic, logical. It has a proof system, which admits a polynomial-time proof search procedure. It has the interpolation property, as my colleague showed earlier this week at VMK. And not only is it decidable in polynomial time, it actually has a normalization algorithm, which when you give it a formula, will find the smallest formula that is equivalent to the input in at most quadratic time. Can we use those properties in some actual applications? So originally, orthologic was used by quantum physicists to describe some quantum phenomena, and more recently by philosophers to describe epistemic logic. And in computer science, we actually used orthologic in a program verifier called Stainless to simplify formula and normalize them with respect to the algorithm I just mentioned to improve the cache-hit ratio and to simplify formulas. Orthologic is also now a core part of the Lisa proof assistance because it is able to take into account automatically a wide variety of syntactically obvious transformations, such as negation, normal form, commutativity, associativity. It makes proofs easier to write and shorter to store and check. But there are also a lot of other possible applications of orthologic that have not been really implemented yet. You could imagine having some type systems with disjunction, union, and negation, where orthologic, the decision procedure for orthologic would give you type inhabitation or efficient decisions for subtyping. Orthologic can be useful if you have refinement types or liquid types in your language, and here maybe efficiency and reproducibility across machines and across versions of systems can be more important than classical completeness. If you have pattern matching, you can use negation to reason about the fact that a certain term is not of a given type. And at the end of this talk, I will show that we can actually use Orthologic as a strict extension of data log. So what's new for today? First, we want to extend Orthologic to support the use of axioms. Then we'll show some proof theoretic properties that this system has, mainly the cut elimination and subformula properties. From those two properties, we'll design a cubic time proof search algorithm with axioms. Then we'll show that there are classes of somewhat interesting formulas that have the same satisfiability in classical logic and orthologic, including two-sat and Horn clauses. So that means that if we use our proof search algorithm for those, we actually find an answer that is also true classically. It has the same semantic. And finally, we'll extend Orthologic with variable and predicate to obtain our little extension of data log. We have some additional results that I won't detail in this talk. So our proof system is sequent calculus based. We note sequence with formulas that are annotated on the left and right hand side, so that phi L psi R is intended to mean that phi is smaller than psi in all ortholattices. So it's a soundness, completeness kind of characterization. So there is a well-known classical sequent calculus, LK, which gives a proof system for classical logic. And it is known that if you restrict it so that every sequence is only allowed to have at most one formula on the right at any given point, you actually obtain a characterization of intuitionistic logic. And it turns out that similarly, if you restrict sequence to contain at most two formulas at any given point, but possibly two on the right, you obtain orthologic. So it's neither stronger nor weaker than intuitionistic logic. So here's a proof system we use. It's classical sequent calculus with the restriction I just mentioned. In particular, observe the cut rule, top left. And then we have an introduction rule for every symbol on both left and right hand side of sequence. And in the end, you have a rule to introduce axioms. That's in the title of this talk. Why are we interested in axioms? Because they make Orthologic more expressive. You can reason given a certain body of knowledge of things that you assume or know to be true. In classical logic, that's not a very interesting topic because you can simply add axioms to the left-hand side of your implications or your sequence, but you can't do that in orthologic. And the intuition is that because of this limitation on the number of formulas you can have in sequence, you can't add as many assumptions as you want left of a sequence. So you need to actually support orthologic the hard way, to support axioms the hard way. Set of axioms that may be interesting are typically some things that are proven by external theorem prover or SMT solver maybe. And the problem we want to solve is given a certain set of axioms that we assume to hold, does a certain other statement always hold? So the first property we need to prove is the cut elimination property. If a certain statement is provable, then it has a proof where the only formulas that are removed by instances of the cut rule are among axioms. So we don't remove anything that is not an axiom. Because the cut rule is the only rule that can remove formulas when read from top to bottom in a proof, we obtain a subformula property, like in the classical case. If a certain sequence is provable, then it has a proof that only uses a subformula of the input. We now use those two properties to design a proof search algorithm. This proof function that takes a sequence gamma delta as input. And it's essentially a backward proof search procedure. So you find all the application of the rules that can somehow conclude with gamma delta, and you recursively solve the premises of those rules. Now, the key observation is that because sequences have only at most two formulas at any given point, and because of the subformula property, we know that this function will never be called on more than n squared different inputs. So if we memorize the intermediate results, we know that we'll never execute the function more than n squared time, whatever the original input is. Now, what is the complexity of one run of this function? It's dominated by the number of rule applications. This is actually a certain constant number, plus one application of the cut rule per different axioms that you could introduce, as per the cut elimination property. So you obtain a final complexity result, which is n squared times the number of axioms. And under some conditions, you can actually obtain n squared. Now we would like to know if there are some interesting problems which orthologic solves exactly with respect to classical logic. And that's the case, for example, of Horn clauses. So if you have a set of Horn clauses, this set is satisfiable in classical logic if and only if it is satisfiable in orthologic. So they have the same meaning. This is also true for two sets, renamed Horn, extended Horn, Q-Horn, some others. Now finally, we want to extend propositional orthologic with predicate and variable symbol, a bit like effectively propositional orthologic, so no function, no quantifiers. And the kind of statement we can encode is, for example, a congruence relation. So you have first the axioms about the equivalence relation, reflexivity, symmetry, and transitivity, and then you can express an axiom for every other symbol in your language and every one of their arity, every place in their arguments that will express the congruence property. And now we can observe that those are actually Horn clauses, so they have the same meaning, the same semantic in classical logic and orthologic. So can we solve those kind of problem in predicate orthologic? Yes, let the degree of A be the maximum number of different variables that appear in the set of axioms. Then we can decide if a certain sequent holds with respect to all the instantiation of this set of axioms in time at most exponential in the degree of A. For comparison, in the classical case, where the equivalent domain is effectively propositional logic, you would have an exponential more in your runtime as far as we know. So finally, we get to a little data log generalization. Data log is effectively propositional logic, so it has only variables and predicates, and formulas are restricted to be Horn clauses. And we know that orthologic is correct and exact for Horn clauses. That means that we can use orthologic with axioms as a strict extension of data log. For the sub-problem that are data log problems, it has actually the exact same semantic. It would solve it the same way as a data log engine. But you can extend and express more things with negation and disjunction. And while here you would not have a classical semantic for those disjunction and negation, you still have a logical semantic, not something based on control flow or execution. And moreover, the runtime needed the complexity of solving such a program would be exponential, similar to base data log. So that's about it. We saw what is orthologic and how it can help with doing formal reasoning predictably and efficiently. We saw that orthologic with axiom admits a cubic time algorithm. We saw some theoretical property of orthologic and effectively propositional orthologic, which in the end led us to a generalization of data log. And I also explained some possible application of orthologic. And yeah, that's it. I'm happy to take questions.
Can you say a few words on the models of orthologics? Like, do you have quick models or anything?
So good question. Models are actually ortholattices. Simply, like the way for classical logic, your models are Boolean algebras, right? So now you have questions about what happens if you try to get full first-order orthologic and what would be your models. In that case, we have some ideas, some things that have been published in the interpolation paper I mentioned. But not complete results about it. We haven't developed Kripke model for those, and it's a bit outside the scope of this approach here.
I understand the lattice model, but is there a way to read the formulas like in natural language, which like and as and or as, because we can't read them that way, I imagine, or we would get distributivity. So how do we understand them intuitively?
Well, a good question. I mean, same as in intuitionistic logic, right? Can you read negation as negation in intuitionistic logic?
Well, I can read and or and implies because I got distributivity and I've got like here.
Right.
Yeah. Another question. So, okay, so you're not giving me an answer that you can read them that way. is there an implication connective in the orthologic?
Good question. So you can define implication connectives in some way. They would not get all the properties you expect from it. In some sense, you have well-defined and well-behaved negation, but not perfectly behaved implication. It's a bit the opposite of intuitionistic
Let me
logic.
ask my question a different way. Do you have a developed, because you use it, do you have a developed intuition where you can stare at formulas and you have a good intuition as to whether they're true or not?
Well, for example, I have some because of training. And it's not so obvious, right? But that's also the case with classical logic. You don't necessarily know. So here's the example we had at the beginning. So I can argue that you can do negation normal form. You can substitute. It has some good properties you expect from classical logic or for our logic. And so you actually can deduce that way that formulas are true. It does not jump to your eyes, but neither does it in classical logic, I guess.
Hi. I was just wondering, do you get other or interesting logics by generalizing this restriction of the number of formulas? So say you generalize and said at most 3 formulas or at most 4 formulas. Do these give you different logics?
That's very interesting. So you could do other things. You can get something dual to intuitionistic if you lock sequence to have only 1 formula on the left. I think that as soon as you have 3 formulas or more, you get classical logic, but I am not completely sure. I haven't showed it properly.
You said for classical logic they have heuristics. My 2 questions. Do these heuristics work for you, and do you have better ones?
Well, the idea is here you don't need heuristics, right? Because you can solve the problem exactly in quadratic time.
N cube with 100 axiom, it will be slow. Huh?
Well, that's a good point. So it would depend on which application, right? Maybe if you have a type system, you don't have hundreds of formulas. But for example, if your axioms has all of the form not of an inequality, but just a single formula that you know how to hold, actually the proof search is done in quadratic time, which is already better. And for some other classes of problem, for example, the unit propagation rule is admissible in orthologic. So if you have some even restricted subset of it, you can actually solve it in linear time. Maybe it would depend on your exact application. But we run some tests, not with axioms, but with the quadratic algorithm. And even like you can normalize formula with up to millions of connectives in instance. Sorry. For applications which were program verification and proof assistance, that was plenty sufficient.
Is there a link between orthologic and effect algebras, which are also close by auto-complement?
I don't know, actually. To be frank, I don't know the topic well enough to answer you on that.
So if you give your solver a formula that is not valid in orthologic, it produces some counterexample?
Yeah, so what you can do is try to normalize it and try to find like a witness, the smallest equivalent formula that is not true, and maybe that is not that is equivalent to your input. Then you can maybe solve it with an external SAT solver if that's what you want, and then you can even reuse it as an axiom for your next the next thing that you can solve. Yeah. So
you can do this kind of relaxation process where you add more axioms.
Yeah, exactly.
Recover the power of classical logic?
Yeah, exactly. Although that would not give you a quadratic time procedure, of course, because you may need to add a lot of axioms for all we know. But that would give you a complete decision procedure, yes, a bit like with SMT solver.
There was maybe a last question. I saw somebody raising it. No takers for a last question? Yeah.
So that's a follow-up question to Odette's. As you said that you would obtain a decision procedure for classical logic by essentially counterexample refinement loop, right?
Yeah.
But has it been tried?
Yes, actually. So I don't want to say that this is competitive. We had a competitive application, but in a proof assistant we did this, and we have actually a method to solve arbitrary propositional tautologies using this. What you do is it's very slightly different, but you normalize the formula, and then you make a decision on some literal, you split it, and you renormalize with respect to orthologic, and so on until you get either a proof or you can't destroy the formula anymore. And as far as I know, this is a little bit more efficient than not using Orthologic. It requires less proof steps.
All right.
Thank you.
Thank you very much.